It was a sunny Sunday afternoon. Favorite Mark was exploring his backyard when his eyes caught a glint of a treasure box he had never seen before.
Go. Sweet. I wonder what this could be.
Favor brought the chest with him inside and quietly opened it.
Whoa.
Congratulations! You have been selected to find the 5 sacred optical devices that have been located in your house. You have 5 hours to locate each of these optical devices and fully understand them.
And who might you be?
Hello, I'm your science godmother, and I've been Simone to help you on your mission for the 5 sacred optical devices.
Today is such a weird day, but if you say so.
Alright, Favor, what's the first hint?
This sacred optical device is used very often in your everyday life. I call it the preserver of memories. Its lens produces a smaller inverted real image of a bigger object. Science godmother, what's a lens?
If I were to ask anyone what a converging lens is, chances are they probably would not know. Look, there's a person. Excuse me. Would you care to explain to us what a converging lens is?
What's a converging lens?
Alright, seems like we need to take this all the way back to the beginning. Lenses are devices that we use almost every day. They gather light and create altered images of objects depending on the type of image that you need. For example, when people use glasses, the lenses in the glasses either make an object seem nearer for nearsighted people or farther for farsighted people.
Oh, okay. That's pretty simple. I get it now.
Hold on, don't get too ahead of yourself just yet. Lenses can get way more complicated than that. There are 2 common types of lenses, converging lenses and diverging lenses. The converging lens looks like this, and the diverging lens looks like that.
Okay.
Imagine it like this. I have a bow and an arrow. And these are my 2 targets. In a converging lens, the bows would hit the target and fly until they eventually meet. In a diverging lens, the bow would not hit the target. It would completely diverge.
Okay, but what does this have to do with lenses?
With lenses, we're not actually dealing with bows and arrows. We're dealing with light rays. In a converging lens, the light rays go through the focal point and go through the center of the lens, where they then meet or converge, hence its name. An image can only be formed once the light rays meet or converge. Sometimes, however, the lines do not converge and will never converge. In cases like this, the image will be formed on the virtual side.
Virtual?
In simple terms, in most cases, the virtual side of a lens is the side of the lens on which the object is on. You can think about it like this. Our eye is looking through the lens from the real world. This is the virtual side of lens that can be seen through the lenses. The lenses is altering our vision of the image. Converging lenses can make a variety of image as opposed to diverging lenses. A good way to tell if a converging or diverging lens has been used is to remember that diverging lenses can only produce images that are
smaller, upright, and virtual. Wait, an object that makes something smaller and inverted it's a camera, isn't it?
Correct. Cameras use converging lenses to produce images that are smaller, real, and inverted. This sketch for an example, but only if the object is at a greater distance than f.
F?
I forgot I was speaking to a child. In a lens diagram, we always have the optical axis. The focus point just represents the place where parallel light rays go through. So in a converging lens, this is the parallel line, and it goes through the f point. And in a diverging lens, this is the parallel line, it diverges and refracts through the f point. There are 2 focuses, f and f prime. F is the point where the light ray goes through, and f prime is basically just the focus, but on the other side of the lens. For a camera to work, the object must always be at a greater distance than f prime. In case you're wondering how the lens diagram for a camera works, this is what would happen. The parallel light ray would refract at the converging lens, and go through F. Then the light ray would go through the optical center. And it will meet right where it's supposed to, between F and 2F.
Alright, so all we need is a camera. Why is it glowing?
Congratulations! You have successfully just found 1 out of 5 of the 5 sacred optical devices.
Yay!
Alright, Faber, what's the next hint?
This device uses converging lens to produce an image that is larger, inverted, and real. Science godmother, I don't really think I could figure this one out.
Oh, come on, Faber, think. Where did you go last Sunday?
Well, last Sunday I went to watch the Batman movie. Wait, could there be a movie projector?
Ta-da! It is!
But how exactly does a movie projector work?
Okay, so do you remember those overhead projectors that teachers used to use all the way back in elementary school?
Yeah, kinda.
So basically, in those projectors, the object is a transparent plastic film of paper with either printed or handwritten text on the sheet. The sheet is then placed on a glass surface with a light source below it and a reflecting mirror above it. The mirror reflects the document onto a bigger screen and makes the sheet appear bigger. It also flips the sheet vertically.
So that's how those images got larger.
The movie projector basically works in the same way. It uses light to create a large inverted real image of an object. Also, for the movie projector to work, the object must be located somewhere between 2F prime and F prime so that the image can be located somewhere beyond 2F.
Got it.
This is how the lens diagram for a movie projector would work. Our image is over here. Remember, it must be upside down for the image to be upright. Refracts at the lens and goes through F. Then we have to draw the line that goes through the center. And here we have the larger inverted real image.
Okay, enough science talk. I think I remember having an old movie projector in my basement. Let me go get it. Ooh, it's glowing again.
Congratulations! You have obtained 2 out of the 5 sacred optical devices. You now have 3 more to locate.
Sweet. Okay, so this next optical device is pretty simple. It produces a larger upright virtual image on the same side of the lens as the object.
Any idea as to what it might be?
Of course, larger and upright. It's obviously a telescope.
You're actually wrong.
What?
Telescopes have 2 converging lenses, which is not what we're dealing with just yet. And they don't produce upright images, they produce inverted images. So try again. Come on, Faber. A device that uses this lens to make something bigger, it's really not that hard, I promise you.
I'm trying, okay?
Okay. Come on. Bigger, larger, magnification.
Oh! A magnification glass. I totally knew that.
Yeah, right.
Oh yeah, it makes more sense to me now. I used to use those things a lot when I was younger. But to be honest, I don't really know how they work anymore.
Excuse me, would you know how a magnification glass works?
You put it on stuff and it magnifies.
Children these days. We use magnification every day. An example is water.
Water?
Have you ever noticed that when a drop of water fell onto a book you were reading, the letter became way bigger?
Yes, that happens to me a lot. But why does that happen?
The rounded shape of the water drop bends light and images of the letters outwards. As it spreads out, the letters appear larger. A magnification glass basically works in the same way. Basically, in the lens diagram of a magnification glass, once the light rays refract, they don't meet. It'll go through the converging lens and then go through F. Then it'll go through the center. No matter how far you extend these lines, they just won't meet.
Wait, but if the rays don't meet, then how's the image formed?
Do you remember when I told you about virtual images?
Oh, yeah.
Basically, what our brain does, it extends these rays backwards and find where the image forms on the virtual side. Remember, virtual rays are always represented by dotted lines. So we extend these rays backwards, and we extend this ray backwards, and it's really easy to see where they meet. And over here, we have our larger upright virtual image.
Okay, I understand. Magnifying glasses are pretty simple. And I know exactly where we can find one. Ta-da! Okay, on to the next one. This optical device uses two converging lenses and produces an image that is upright, larger, inverted, and virtual. Oh, you mentioned something about two lenses before. It's a telescope, isn't it?
You're actually wrong. The
What?
optical device that we're dealing with helps us see nearby objects, and telescopes help us see faraway objects.
Well, in this case, it has to be a microscope, right?
You are correct.
If you think about it, microscopes work almost the same way as magnifying glasses.
Yes, you're actually correct. The compound microscope works a lot like the magnifying glass, but way more complicated. As you may have already heard, the compound microscope uses two converging lenses. One is the objective lens, and the other is the eyepiece lens. The objective lens produces a real image, but we can't see that image because it's inside the body of the microscope. The eyepiece lens produces the virtual enlarged inverted image, which is the image that we see.
Okay, so if both lenses produce images, why can't I see the real image? How is it in the tube?
Alright, so think about it like this. If I were to yell inside a folded piece of paper, what type of sound would come out?
A much louder sound.
Exactly. But what you can hear is the sound that I originally made, my normal voice. And why is that? Because it's inside the tube. You can only hear the sound that has been altered to be made much louder. This is a lens diagram for a compound microscope. First, we draw a parallel light ray that goes through F. And then we draw the other light ray that goes through the center. As you can see, they form somewhere over here. This is the real image that was formed by the objective lens. Next, they go to the eyepiece lens, where they refract again. They meet over here where the virtual image is formed.
Now that I fully understand how a compound microscope works, now it's time to start looking for one. Where could it be? Oh wait, I found it. Here's the microscope. Okay. This optical device produces a larger inverted virtual image. I bet she's waiting for me to slip and say telescope again. But I won't say it.
Do you know what it is?
Few minutes later, a little longer than a few minutes later.
Come on, Faber, you still don't get it? It's a telescope!
Are you being for real? Okay, so I bet what you're gonna tell me is that telescopes work the exact same way as microscopes, except this time the object is far away, right?
Wow, you finally got something right. Okay, so Faber was correct. Just like microscopes, telescopes have two converging lenses. One makes the real image that we can't see, and the other makes the virtual image, which is the one that we can see. The lens diagram of a telescope basically works the same way as the lens diagram for a microscope, except for one small detail. The object in the telescope is so far away. Because of this, the light rays that refract are parallel. They're parallel because they're so far away. And go through F. The real image, let's say we're using the moon as an example, is going to meet somewhere over here. Next, the light rays are going to refract at the eyepiece lens. When they refract, the virtual image is formed. And this is where our enlarged virtual image is formed.
Yeah, I get it now. Wait, does that mean that I get 500 coins now that I'm done?
Yes, but we have to find the telescope first.
Whoa, I found my telescope, and it's glowing. Thank you so much, Science Godmother. I couldn't have done it without you.
No problem, Favor. I'm really proud of you. But it's time for me to go back to my physics home.
Whoa, she's disappearing.